Beneath the floor of a modern electric vehicle lies an engineering marvel that weighs over half a ton, the battery pack. This isn't just a collection of batteries, it is a high-voltage monolith designed to withstand extreme crashes, torrential rain, and the blistering heat of rapid charging for over a decade. To the naked eye, it looks like a simple metal slab, but inside, over 5,000 components work in perfect harmony. We are talking about a system that manages enough energy to power an average American home for 4 days, yet it must discharge that power in seconds to propel a 2-ton vehicle from 0 to 60. The precision required here is staggering. We are measuring tolerances in microns because even a single loose connection could lead to a catastrophic failure. This is the story of how sand, lithium, and cobalt are transformed into the beating heart of the electric revolution. From the raw chemistry of the individual cells to the complex thermal management systems that keep them cool, we are going inside the Gigafactory to see how the world's most advanced energy storage systems are built. It all begins with the cell, the fundamental building block. Inside a climate-controlled cleanroom, giant rolls of copper and aluminum foil, thinner than a human hair, unspool at high speeds. These act as the current collectors. On one side, a dark slurry of anode material, typically graphite, is coated onto the copper. On the other, the cathode, a precise mixture of lithium, nickel, manganese, and cobalt, is applied to the aluminum. This isn't just painting, it's a high-tech chemistry experiment performed at an industrial scale. The foils pass through massive drying ovens, hundreds of feet long, where the solvents evaporate, leaving behind a perfectly uniform layer of energy-storing material. Next comes the calendering process, where massive rollers compress the coated foils with thousands of pounds of pressure. This increases the energy density, packing as many ions as possible into the smallest space imaginable. If the thickness varies by even a few micrometers, the cell's lifespan will be compromised. Once compressed, the foils are slit into precise widths, ready to be wound or stacked into the cylindrical or prismatic shapes we recognize. With the foils prepared, they are layered with a porous polymer called a separator. This thin plastic sheet is the only thing standing between a functioning battery and a short circuit. It allows ions to pass through while keeping the anode and cathode from touching. In a process known as winding, these layers are spun at incredible speeds into what engineers call a jelly roll. This roll is then inserted into a nickel-plated steel can. But it's still just a dry assembly of metal and plastic. To bring it to life, an electrolyte, a conductive liquid, is injected into the can. This liquid fills every microscopic void between the layers. Finally, the cell is sealed with a cap that includes a safety vent. This vent is a critical piece of engineering, designed to rupture and release pressure if the cell ever overheats, preventing an explosion. Each cell is then laser welded shut with a beam thinner than a needle, ensuring a permanent airtight seal that must last for the entire life of the vehicle. The cells are now physically complete, but they are chemically asleep. To wake them up, they enter the formation phase. This is the first time the cells are ever charged. It's a slow, delicate process that takes hours, carefully building up a protective layer on the anode called the solid electrolyte interface, or SEI. This layer is crucial. It acts like a filter, allowing lithium ions to pass while protecting the graphite from the electrolyte. After formation, the cells aren't sent straight to the assembly line. They must age in massive, climate-controlled warehouses for up to 3 weeks. During this time, sensitive sensors monitor every single cell for even the slightest drop in voltage. A drop of just a few millivolts is enough to trigger a rejection. This ensures that only the most stable, high-performing cells make it into the final battery pack. Out of millions of cells produced, only the elite are chosen, because in a battery pack, you are only as strong as your weakest link. Individual cells provide about 3.7 volts, not nearly enough to move a car. To get the power we need, we group them into modules. High-speed robots pick up rows of cells and slot them into high-strength plastic frames. These frames act as both insulators and structural support. Imagine a Lego set made of live electricity. Within each module, cells are connected by bus bars, thin plates of highly conductive copper or aluminum. Instead of traditional soldering, which generates too much heat, a high-frequency laser or ultrasonic welder taps each cell to the bus bar. Thousands of these tiny welds are performed every hour, each one checked by an AI-driven vision system for perfect conductivity. This architecture allows the module to act as a single, powerful battery unit. It's here that we also integrate the first layer of monitoring, small sensors that track the temperature and voltage of each cell group, reporting back to the car's brain 40 times every second.
Heat is the enemy of performance. When you accelerate hard or use a supercharger, the batteries generate immense amounts of thermal energy. To prevent them from degrading, we need an advanced cooling system. Engineers weave cooling ribbons, thin, hollow aluminum tubes, between the rows of cells. A specialized thermal interface material, often called gap filler, is injected around the cells. This gooey substance makes sure there is perfect contact between the cell and the cooling ribbon. A mixture of water and glycol, similar to what's in a gas car's radiator, is pumped through these ribbons. This system is so precise it can maintain the entire pack's temperature within a window of just a few degrees, whether the car is in a sub-zero Alaskan winter or a scorching Mojave summer. Without this thermal management, the battery would lose capacity in just a few years. With it, the pack can easily outlast the car itself.
The modules are now ready to be housed in the battery tray. This isn't just a box, it's a structural component of the vehicle's chassis, often made of high-strength extruded aluminum or even cast titanium. This tray must protect the cells from road debris, water, and side impact collisions. The modules are lowered into the tray by heavy-duty robots, then bolted down to provide maximum rigidity. Running beneath the modules are the high-voltage cables, thick, orange-shielded copper wires that carry hundreds of amps of current. These lead to the Battery Management System, or BMS, the pack's brain. The BMS is a sophisticated computer that balances the charge between every module, ensuring no single group of cells is overworked. It also controls the contactors, massive high-voltage switches that can instantly disconnect the pack from the car in the event of a crash, cutting the power in less than 20 milliseconds. Before the lid is closed, the pack undergoes a final, meticulous inspection. Technicians use infrared cameras to check for hotspots and high-resolution scanners to ensure no debris was left inside. Once cleared, a robotic arm applies a specialized silicone sealant around the perimeter of the tray. This seal must be perfect. It has to keep out moisture and dust for 300,000 miles of driving. The top cover is then lowered and secured by hundreds of high-torque bolts, tightened in a specific sequence to prevent warping. Finally, the pack is pressurized with air to check for leaks. If the pressure drops even a fraction of a PSI over several minutes, the pack is pulled from the line. It must be completely airtight, literally capable of being submerged in water without a single drop reaching the high-voltage electronics. This is the last line of defense for the energy stored within. Before any pack is shipped to the vehicle assembly line, it faces a gauntlet of torture tests. Randomly selected units are placed on shake tables that simulate a lifetime of driving over cobblestones and potholes, vibrating the pack with violent force for hours. Others are placed in thermal chambers, rapidly cycled from -40 degrees to over 140 degrees Fahrenheit. We even perform end-of-line electrical tests, where the pack is hit with a massive surge of power to ensure the internal fuses and contactors function perfectly. This is industrial-grade paranoia, because when you are dealing with this much energy, there is zero room for error. Every bolt, every weld, and every drop of coolant must perform its job flawlessly. Only after passing these rigorous checks does the battery receive its digital birth certificate, a unique ID that tracks its health for the rest of its life. The finished battery pack is now ready to be mated to the car. In many factories, this is known as the marriage, where the battery is bolted to the chassis, becoming the floor of the vehicle. This low placement gives electric cars their famous low center of gravity, making them incredibly stable and safe. What started as raw powders and thin foils has become a sophisticated energy machine. This single unit represents the work of thousands of engineers, chemists, and software developers. As it rolls off the line, it's ready to provide clean, silent power for hundreds of thousands of miles. Eventually, when this pack finally reaches the end of its life on the road, it won't be thrown away. It will be recycled, where nearly 95% of its materials, the lithium, cobalt, and nickel, will be recovered and sent back to the start of the line to become the next generation of batteries. This is the circular economy of the future, built with the precision of the present. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.